Welcome to this Forge College Explainer. I am absolutely pumped to have you here today. If you're tuning in, it means you are elbow deep in the From EVM to SVM track, specifically the Designing Solana Contracts from EVM Counterparts module, and you are ready to roll up your sleeves. Now, in our previous lesson, we mapped out state and ownership patterns. We figured out what goes where, mostly in theory, but today we're taking those mapping choices and turning them into a concrete, actionable blueprint. Think of this as stepping out of the conceptual phase and right into the architect's studio. We are going to draft the literal foundation for your capstone project, porting an EVM project over to Solana. Let's get to work.
To get us in the right mindset, let's take a look at the massive philosophical shift we're making here. On the left side of our blueprint, notice the classic EVM approach. On Ethereum, we've got this really strong tendency to just hoard absolutely everything into a single giant monolithic contract. State, logic, variables, user balances, it all goes in there. It's kind of like a massive, slightly overstuffed Swiss Army knife. Sure, it does everything, but man is it heavy and incredibly complex to upgrade. Now look on the right at Solana's approach. The SVM relies on a totally elegant, decoupled architecture. It's way less like a Swiss Army knife and much more like a highly specialized assembly line, where your executable code is completely separated from the accounts holding your serialized state.
Okay, let's dive into our agenda for today. To build out this new assembly line, we need to master three core architectural pillars. First up, program decomposition. Second, account grouping. And third, instruction composition. And finally, we'll bring the whole shebang together by blueprinting an actual ERC20 flow.
Let's step right up to the drafting table and tackle pillar number 1, program decomposition, or how we split that monolith.
When you leave the EVM, where your storage and functions were happily bundled together, you immediately hit a pretty big decision point. Do you build one giant Solana program to handle everything, or do you design several specialized, smaller widgets that talk to each other? Well, you've got a few distinct options on the board here. You don't actually have to split everything up. If you have a small contract with tightly coupled state, a monolithic program might be absolutely perfect. It gives you a simpler ABI and a single upgrade path. But if you have distinct domains, say a token, a lending pool, and a governance module, you are really going to want the modular programs approach shown in the middle row here. The pro? A beautiful separation of concerns. The con? You'll have to rely heavily on cross-program invocations, or CPIs, which require some really careful orchestration of authorities. There's also the program plus wrapper approach, giving you a stable core but with flexible UI and UX changes. Your job as an architect is to match the pattern to your specific porting scenario.
Moving right along to our second pillar, account grouping, or as I like to call it, packing the gears.
Once you know where your code lives, you have to decide exactly where the data lives. On Solana, how we pack our state data dictates not only how fast our program runs, but also how much it literally costs to deploy and maintain. When grouping data, you generally have two main paths. On one hand, you have per-user accounts. Imagine every single user getting their own individual, neatly labeled data file. This allows for incredibly high concurrency. Literally thousands of users can transact at the exact same millisecond because they aren't touching the same accounts. But it means higher rent costs, since every new account needs a minimum balance. On the other hand, you have aggregated maps, which is basically putting everyone's balances into one big shared account. This costs way less in rent, but it introduces a massive bottleneck. If everyone is trying to update that single account at once, your transactions are going to fail due to high contention. It's a classic trade-off.
And you know, we absolutely cannot talk about data without bringing up the sheer joys of calculating rent exemption. On Solana, you literally pay for the space you take up on the network. This isn't just an afterthought you can push to the end of the project. Your account sizing choices directly constrain how you group data. If you blindly port an EVM mapping into millions of individual Solana accounts without thinking about the rent exemption math, well, your project is going to run out of funds before it even gets off the ground.
So to make this data grouping work securely, we need our essential inventors tool, the program-derived address, or PDA. A PDA is an address designed specifically to be controlled by a program, not by a user holding a private key. It's deterministic, meaning we can derive it using specific seeds, like a user's public key, or even a simple string like escrow. PDAs are the absolute backbone of representing program-controlled state and handling authorization on Solana. You are going to be using these constantly, so get comfortable with them.
All right, we've got our programs and we've got our accounts mapped out. Now we arrive at the third pillar, instruction composition. I like to call this the atomic dance. This is the art of figuring out how we compose our newly decoupled accounts and programs so that they work together flawlessly and, most importantly, safely in a single atomic transaction. To orchestrate that atomicity on Solana, you have to follow strict design rules. First, you must pass all relevant accounts to your instruction upfront. Second, your instruction handler must perform all state updates before returning. And third, you must carefully order your authority checks. So the crucial point here is that if any single step fails, the whole transaction rolls back entirely, which perfectly preserves the safety invariants you relied on in your EVM original.
Okay, enough theory. Let's zoom in on a specific section of the blueprint and see this in action.
We are going to apply these 3 pillars by porting a complex EVM ERC20 contract. One that doesn't just transfer tokens, but also features an escrow mechanism and role-based access control. In Solidity, this would likely just be one single file, packed with a bunch of mapping statements. But applying our SVM decomposition, we split this monolith into specific, isolated core domains. We break it down into a token ledger holding the mint account and per-user balances. We carve out explicit PDAs for allowances. We create entirely separate PDAs for escrow records, complete with their own release timestamps. And we isolate the role metadata into its own small, tight registry.
Let's look at the actual data structures for this. Notice in this dark green technical sketch of our anchor structs here, we have explicitly separated the token mint from the user account. The token mint holds shared metadata, like who the overarching authority is and the total supply. Meanwhile, the user account holds only the individual's balance. Why do it this way? To minimize transaction contention. If user A transfers to user B, they only lock their 2 specific user accounts. They don't block user C and user D from transacting at the exact same time. It's brilliantly efficient.
And this brilliantly illustrates our point about PDAs. Look at this sketch of the allowance PDA struct. It contains the owner, the spender, and the allowance amount. But its authority doesn't come from a private key. It derives its authority directly from the program logic, using the owner and spender public keys as derivation seeds. Anyone reviewing this technical blueprint can see exactly how the authorization flows deterministically, right there in the ink.
Now let's map out the multi-step flow for a transfer that also includes a fee. In our atomic dance, Step 1 checks the allowance, Step 2 subtracts from the sender's balance, Step 3 adds to the receiver's balance, and Step 4 updates the shared fee pool. Because of how we've so carefully grouped our accounts and composed our instruction, all of these actions happen in one seamless atomic swoop. There are literally no vulnerable intermediate states where an attacker can slip in and mess with the logic.
To guarantee that atomic swoop, your instruction context must be perfectly defined. Look at the mute keywords sketched out here for the sender, receiver, fee pool, and allowance accounts. By explicitly requiring all these accounts as mutable, right alongside the external spender signer, you are forcing the Solana runtime into a strict binary outcome. Either it executes the entire multi-account atomic flow perfectly, or it immediately rolls the whole thing back. No half measures.
As we pull back from the intricate details of the blueprint, let's quickly recap the 3 guiding principles you are going to use to create your high-level redesign sketch. First, align your account grouping with your access patterns. Use per-user accounts for concurrency or shared accounts for lower rent. Second, comprehensively document your explicit authority flows. Write out those expected account sizes and PDA derivation seeds for your peers to review. Third, always prefer atomic single instructions where possible, saving those complex CPIs for when domains truly, absolutely need to be separated.
Which brings me to you and your capstone project. How will you sketch out your core instructions? Are you going to build a monolith or a beautifully decoupled assembly line? What seeds are you going to use for your PDAs? Take these principles and start drafting. I want to remind you that this explainer was proudly made by Forge College. For deeper technical breakdowns, full courses, and to really master these Web3 architectures, I highly encourage you to visit forge.college to learn more. Happy building, and I will see you in the next lesson.